Hi everyone, we're solving this physics paper today. This is 9702 paper 52, October November 2023. The time is 1 hour 15 minutes. This is paper 5, planning, analysis and evaluation. So we have two parts to this question paper, Q1 and Q2. Before we begin, let's take a look at the threshold. But before that, I'd like to give a quick shout out to my patron. If you guys like the videos, please do remember to subscribe to the channel, turn the bell on for all notifications. And on Patreon, you actually get access to 3 tiers. You can choose to support me here. For the first tier, it's just general support regarding question papers and exam prep techniques. For the second tier, you get access to all of these question papers, solved question papers from 2002 to 2023 for physics, chemistry, and bio, paper 1, 2, 4, and 5, and math P1, P3, M1, and S1. So I think this is an amazing deal. You should go for this. If you need the help just before your exams, you can just subscribe to it for like 2-3 months, get access, and just give the exam. And for the last year, you have the ultimate learning experience, which is $50 a month, but you get access to one-on-one video meetings with me via Google Meets once or twice a month, where we can solve your personal problems, which is insane. Anyway, let's take a look at the threshold. So this is paper 5.2, right? Component 5.2. I actually solved component 5.1 recently, 5.1 or 5.3, it's the same one. So out of 30, A is at 23, B is at 21, C at 18, D at 14, and E at 11. So 23, 21, 18. Let me write this down. The highest mark is 30, out of which, A is at 23, B is at 21, A is at 23, B is at 21, C, D, and E. Sorry, 18, 14, and 11. 18, 14, and 11. So it should be around 3 marks higher. 2 to 3 marks higher, like 25 or 26, somewhere here. That should be the value for A star. By the way, I do plan to solve chemistry paper 5 soon, as well as bio paper 5, and physics paper 4 as well. You will be getting those before your May June 2024 exams, hopefully. Basically, I will be a lot more free starting from May, since I will be letting go of tutoring, private tutoring, which I do here in Bangladesh. So I can focus more on YouTube and my career as a doctor, because I'm going to be a doctor this year. So that's also awesome. So yeah, let's see where it goes. I have huge plans. The channel has been getting a lot of reach recently, without any advertising or promotion. So if you guys do want to support this content and want me to make more, please do share this with your friends, like the video, subscribe to the channel. It helps a lot, actually, a lot. Okay, so without further ado, let's begin. Starting with question 1. Two identical beakers, each of mass m, are attached to each other using string and suspended from a pulley as shown in figure 1.1. The beakers are held at rest at a height h above the surface. Cooking oil of volume v is added to one of them. Okay, so this is like mechanics, pulleys. The beakers are released so that the beaker with the oil begins to fall. The speed of the beaker as it reaches the surface is z. It is suggested that z is related to v by the relationship 2h by z square is equal to 2m by abv plus 1 by b, where a and b are constants. This is a key point, where a and b are constants. Plan a lab experiment to test the relationship between z and v. So one of them is the dependent variable while the other is the independent variable. So let's see how to figure this out. Always think of it chronologically. Which one comes first, okay? Between z and v. So what is v? V is the volume of cooking oil that is added to one of the beakers. And what is z? The speed of the beaker as it reaches the surface is z. So obviously, you are going to add cooking oil first, and then the beaker will fall down with speed z, right? So v comes first, followed by z. So we should write that v is the independent variable and z is the dependent variable, because z actually depends on v, how much volume we put in, right? Now, what do we need to keep constant in the experiment? So not z and v, right? Since they are variables, then not 2 either because it's a constant, not A and B either because those are constants as well. 1 is also a constant. So what do we need to keep constant? H and M, right? H and M need to be kept constant in this experiment. H and M. Okay? So that's the first part. Now let's talk about methods of data collection. How are we going to measure V and Z? So clearly, V can be measured using a measuring cylinder. If it was chemistry, you would have to use a burette or something, right? And to measure Z, since it's a fast moving object, we actually need to use light gates at the end of the, close to the ground. That is light gates connected to a timer or connected to a data logger to measure the speed. And we need, how are you going to measure H? H is the height above the surface. So we can actually use ruler because we need to keep this constant, right? We can use a ruler that is attached to a clamp, and we can ensure that it is perpendicular using a set square. And what is missing in the diagram? The pulley requires a support, right? So we actually need a support and the labels. So that's part of methods of data collection. How you're going to measure V, Z, H, and the diagram itself, okay? So here you go. The red part is defining the problem. V is the independent variable and Z is the dependent variable. Or you can say vary V and measure Z. Keep H constant was part of defining the problem. And keep M constant. Although I did mention it before, it is actually part of additional details. Okay, so that is 1 point out of 6 that we can write in additional details. For methods of data collection, we can use a measuring cylinder to measure V, use a meter rule to measure H, which can also be drawn in the diagram, use light gates connected to a timer or a data logger to measure T, time T, the time of fall of the beaker. So here's the thing, you can't actually use light gates to measure velocity, Z. Okay, Z can't be measured directly. It needs to be calculated. How? We know that speed is equal to distance by time. So actually we are using the light gates connected at the end, right? Only to measure the time taken for the fall. For that short distance over here, right? And then to find out velocity, you can just go for distance by time, okay? And how are we going to measure M? M is a mass. We can use a top pan balance or just a balance works. So see if this is fine. This is the diagram. You need a stand that is connected to the pulley to support it. You need to label the beakers, the string, the pulley. Then you gotta label the surface or the table. You can draw the ruler which is supported by a clamp. You can draw the light gates close to the beaker that is actually falling. Okay. Is this fine? So for methods of the data collection, you have 4 points, right? The diagram itself, this diagram, okay. What else do you need? Wait, let me fix this. That's that. And you have measuring cylinder to measure V, meter rule to measure H, light gauge to measure the time of the fall for that short distance that I marked with the green arrow, and the top pan balance to measure M, okay? So let's talk about additional details now. So clearly, since there are falling objects, we should actually use, you know, cushion or foam or a sand tray or something, sandbox for the falling beaker so that there is no spillage of oil. And there was actually 2 points for safety. We could actually talk about wearing gloves to avoid contact with the oil since this is cooking oil, okay? Then we said that we will keep M constant and we will use a top pan balance to measure M. So we can also measure that. Why don't I just, write this point over here? I think it should be better, right? Use a top pan balance to measure M. I think this makes it better. So those two are actually additional details, yeah? Keep M constant and use a top pan balance to measure M. And use a sand tray or cushion for the falling beaker to land to prevent spillage of the oil or any injuries and use gloves to avoid direct contact with the oil. Then we will say how we measure Z actually. Okay, so Z is measured using this formula. Distance between the light gates, this green arrow, divided by the time taken for the fall between those light gates, which we use the light gates connected to the timer to figure that out actually. So that's how we can find out, calculate Z. Then what else? I told you this before. We can use a set square to ensure that the ruler is perpendicular to the surface, or you can just clamp it. Clamp the meter rule with a stand on the surface. Same point. You don't get 2 marks for this. And there's the common point that you can repeat experiments, repeat the measurements of Z for the same value of V and average Z. Okay, so this will always be fixed. Repeat measurements of the dependent variable for the same value of the independent variable to get an average value of the dependent variable. Okay, so using the same independent variable, we are going to repeat measurements of the dependent variable and average it. That is the main thing here. So since V is the independent variable, I'm saying for the same value of V, repeat measurements of Z and average it. Essentially, that is the point. And how to reduce error? Basically, we need a larger value of Z. Okay, so how to do that? If you use a larger value of H, if you increase the value of H, then the beaker will have a longer time to fall. It will increase its velocity. So percentage error will decrease. That is the gist. And you can give a detail about how to keep H constant. We can use a fiducial marker to release the beaker from the same position, or you can release it from the same position on the clamped ruler each time. Basically, suppose if this is at 30 centimeters, you can always, balance the beakers at 30 centimeters and then let it go every time. That's how you can ensure that it's released from the same height. Does that make sense? Anyway, you didn't have to write so much. You can only get a maximum of 6 points, right? So you have 2 here, 3 here, 4 here, right? And then 5, 6, 7, 8. There's one more here. And there's another point, okay? There's another point. Let me see. There were 2 points for safety, 2 points for M. How to keep H constant, there's a formula. How many did I count over here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yeah, there's 9 here. So the last one is actually when the relationship is valid. Okay, so I'll show you. Anyway, let's start with the analysis. So what is our goal here? Since Z is the dependent variable, it should be on the left hand side. So I'm going to put everything else. I'm going to put everything else on the right hand side, which is 2h. So 1 by z square is equal to 2m by ab v into 2h plus 1 by b into 2h. So let's go. We can get rid of 2. Okay. Yeah, I guess that's it. 1 by z square is equal to 1 by v. And here we have m by abh plus 1 by 2bh. So this is it. This is it. This is the analysis. 1 by z square is equal to 1 by v times m by hab plus 1 divided by 2hb. So we are going to plot a graph of 1 by z square against 1 by v. That is the first point. And the relationship is valid if a straight line is produced that does not pass through the origin and actually passes through the intercept of 1 by 2hb. So that is an additional detail here, not part of analysis, because they ask you to find out 2 constants. If they ask you to find out 2 constants, okay, then this point is actually part of additional details rather than analysis. Now we are going to say how we find out a and b. So 1 by 2hb is equal to the y-intercept. So if you make b the subject by algebra, b is actually 1 by 2h times the y-intercept. And on the other hand, m by hab is the gradient, so a will actually be equal to m by hb times the gradient. So that is it for the analysis. If you guys need to copy anything, here's the last look at it. You can take a screenshot or something, pause the video, copy it. But yeah, this is how it should be done generally. Very concise, and I think it was pretty easy. Comparatively, this was an easy question, in my opinion. I think pretty straightforward kinematics experiment. And I think we should move on to question 2 now. So question 2 is actually on capacitors. A student investigates the discharge of capacitors in the circuit shown in figure 2.1. The capacitors have capacitances CA and CB. The student closes the switch to charge the capacitors. The switch is opened and the stopwatch is started. The capacitor is discharged through the resistor of resistance R. At a fixed time t, the voltmeter reading V is recorded. The experiment is repeated for different values of capacitance Ca and Cb. For each combination, the combined capacitance is calculated, and it is suggested that C and V are related by this equation. V is equal to I naught e to the power minus t by Rc. You guys know this already. Discharging a capacitor, the formula V equals to V naught e to the power minus t by Rc. V naught has just been written as I naught times R, where I naught is the initial current in the resistor. So do you guys get what happens? So when we close the switch, the capacitors charge up. But when you open it, what will happen? The charge will actually discharge through the resistor. And we repeat this process. And we actually measure the voltage V at a certain time. Right? So graph is plotted of ln V against 1 by C on the x-axis. So why don't you introduce ln? You get ln V equals to ln I naught R e to the power minus t by RC. I break it down. Ln V equals to ln I naught R minus or plus ln e to the power minus t by RC. Ln e can be written as 1 and the power comes down. Minus t by RC comes down. So we have ln V is equal to minus t by R times 1 by C plus ln I naught R. So here, minus t by r is our gradient, while ln I naught r is the y-intercept. Hopefully you guys understand. Okay, so that's good. So let's move on to the next part now. Now we need to fill up the table. Values of CA, CB, and V are given in table 2.1. So let's see how to do this. So combined capacitance for series. For series, the formula will be like this. It is the reciprocal addition of the reciprocal 1 divided by CA plus 1 divided by CB to the power minus 1. 1 by CA plus 1 by CB to the power minus 1. So let's do that. These have powers of 10 to the power minus 4. So what will you do? It is basically 1 divided by 2.2 into 10 power minus 4 plus 1 divided by 2.2 into 10 power minus 4. Oh, they don't want the combined capacitance actually. They just want the value of 1 by C. Because 1 by CA plus 1 by CB reciprocal is C. So if you get rid of this to the power minus 1, you are going to get 1 by C. Hopefully that makes sense. So we don't need to do the reciprocal, we just need to add the fractions. Okay, they want the reciprocal of 1 by capacitance. The formula is given like this. I personally don't like it much. They want you to do this. 1 by CA plus 1 by CB is equal to CB plus CA divided by CACB. Or you could just do this directly. This is fine. Same thing. Try doing this and try doing this. You will get the same answer, okay? So what are we getting? We actually get a value of, for the first one, it's 9090, but as you can see, the power above is 10 to the power 4. So if you have a power of 10 to the power 4 over here, you are supposed to do the opposite over here, okay? So if you multiply this by 10 to the power minus 4, then you are going to get the answer. So this into 10 to the power minus 4 is equal to 0.909. So since the data is given to two significant figures, you can give the answer to 2SF or 3SF. So I opted for a 2SF answer. So it's going to be rounded off to 0.91 into 10 to the power 4. 0.91 times 10 to the power 4. That will be on the top though. We don't show it. So let's do another one. For example, let me show you this one, 5.6, okay? So I'll show you both formulas. Okay, check this. So 1 divided by 5.6 into 10 power minus 4 plus 1 divided by 5.6 into 10 power minus 4. Try doing this. 1 by 5.6 into 10 to the power minus 4 times 2. That gives me an answer of 3571.429. So times 10 to the power minus 4 is 0.3571. We can write this as 0.36. Okay. And if I use their formula, this one that they gave here, 5.6 into 10 to the power minus 4 plus 5.6 into 10 power minus 4 divided by 5.6 into 10 power minus 4 whole square. So let's do that. 5.6 into 10 power minus 4 plus 5.6 into 10 power minus 4 divided by 5.6 into 10 power minus 4 whole square. So that gives us an answer of 3571. Same 0.429, same answer. So it's up to you guys, whichever route you want to follow. I won't stop you. Anything works, okay guys? Anything is fine. It's up to you, don't worry. So yeah, so we do that for all the values. You can match then afterwards. And for v, we have ln v. So the rule for ln is a bit different. Basically, for ln, the number of significant figures in the data determines the number of decimal places in your answer. So since you have 3 significant figures in the data, you can give your answer to 3 decimal places or 4 decimal places. Okay? So since you have 3 significant figures in the data, you can give your answer to 3 dp or 4 dp. Okay? So it's 2.45, which is 3SF, so I can give an answer to 3 dp or 4 dp. So let's try. Ln 2.45 is 0.896 or 0.8961. These are your options, 3 dp or 4 dp. I opted for the 3 dp answer, which is 0.896. Okay, so what I opted for the 3 decimal place answer, 0.896. So what about the uncertainty though? It's log or ln, depends on the question. It's ln upper bound minus ln lower bound. Okay, so for example, here we have ln upper bound, which is 2.45 plus 0.05, 2.50, minus ln lower bound, which is 2.45 minus 0.05, which is ln 2.40. So ln 2.5 minus ln 2.4 divided by 2, which is 0.0204. So I opted for the same number of decimal places, so I kept it as 0.020. If you wrote 0.8961, it would be better to keep it as 0.0204. Make sense? And then I applied it for the last one as well, which is ln 3.85. I kept it as 3 dp answer, 1.348, not the 4 dp one. And the uncertainty is ln 3.9 minus ln 3.8 by 2, which is 0.01299, 0.01299. Or it can be rounded off to 0.013. Is that fine? Okay. So you can check the other ones. If you have any queries, please do comment below. Moving on to the next part. Now we have to plot the graph of ln v against 1 by c. So ln v against 1 by c, as you can see, it's drawn here. So you can take a look at the points first. Here you go. These are the points. Ln v against 1 by c. Ln v against 1 by c. So ln v, take a look at the first point, 0.896. It is at 0.91. So 0.91 is over here, 0.91, and 0.896. Where is that? 0.896. This is 0.86, 87, 88, 89. So 896 should be somewhere around here. This is 895. So 896 is somewhere around here. So it's just above 0.895, 0.896. Then you can go to the next point. And you can also look at the error bar. It's plus minus 0.020. Since it's on, the error bar is at ln, so it will be a vertical line. So it will go up, you know. Basically, it's 2 small boxes is 0.010. So 0.020 will be 4 small boxes. So 1, 2, 3, 4 up here, and 1, 2, 3, 4 down here. and then the next point 1.012 at 0.76. So at 0.76 over here, you got 1.012, 1.012. This is 1.01, this is 1.02. 1.012 should be somewhere over here, and it's basically plus minus 0.018. So if you add this up, it actually goes up to 1.030 up top, and below it actually goes to, let's do the math, wait, 1.012 minus 0.018, it actually goes to 0.994. Okay, so I drew it somewhere around there, 0.995 ish. Then you have two other points, 1.115, 0.63, and 1.131, 0.61, 0.63 third one, and 0.61 first one. Okay, there you go. So, and 1.115, you can draw that exactly, and it's plus minus 0.016, both of them. So one actually goes up to 1.131, and the other one actually goes to, let's do the math, 1.115 minus 0.016, which is 1.099, 1.099, which is basically 1.10, essentially 1.10, 1.099. So yeah, and as you can see, the rest are drawn, 1.253 at 0.48 and 1.348 at 0.36, 1.36, yeah. So that is that. And you can draw the error bars afterwards. According to my diagram, it should be close enough. And then we have to draw the worst acceptable line and the line of best fit. So as you can see, this is my line of best fit. It passes through the first point, goes below the second, above the third and fourth, goes through the fifth, and below the sixth. So it is above the third and fourth and below the second and last point. Okay, so there's complete balance, and you can check your line of best fit. It's supposed to pass through these points. Okay, let me check the mark scheme. It says wait, it should pass through 0.820, 0.820 and 845 at 0.95, 820 and 845 at 0.95, and 0.40 and 0.425 at 1.30. So you can check your diagram whether it passes through these black lines that I drew. Okay, and for the worst acceptable line, I chose to draw the steepest line, so it passes through the upper bound of the first point and the lower bound of the last point. And yes, it does pass through all error bars. If it didn't, I would edit the line slightly. Then I drew the dotted triangle. It is recommended that you draw it and only use crosses or dots to plot the points, by the way, and draw the error bars like I did. Okay, you could also draw error bars like this. I have seen this being accepted in some mark schemes like this. This is also fine, but I prefer my one. Anyway, draw the dotted triangle. Dotted triangle. I chose this point over here. I draw one triangle which is common to both lines, and then I recorded the coordinates. Do this with a pencil. The only labels on your diagram should be the line of best fit and the worst acceptable line. So these are my coordinates, and remember there's a power for the x-axis points. Okay, so for this we have 0.88 at 0.91, and this is 0.87 at 0.91. Okay, and here it's 0.4 at 1.325 for the worst acceptable and 1.315 for the best fit. Now I just input this in the formula for gradient. Okay, so 1.315 minus 0.91 divided by 0.88, 0.4 minus 0.88 times 10 to the power 4, of course, since there's a power here, and I get the gradient for the best fit line. You repeat it for the worst acceptable line, and to find out the uncertainty, it's just basic subtraction of the magnitudes. Yep. So I get something like 3.9229 times 10 to the power minus 6. Then I adjust the power accordingly so that it matches the gradient of the best fit line. And then I write it as, you can give your answer to 2SF or 3SF starting from the gradient onwards. I chose 3SF. So that is minus 8.44 plus minus 0.39 times 10 to the power minus 5. That is my gradient. Okay. Let's move on to the next part then. Last page. Let's wrap up soon. Determine the y-intercept of the line of best fit. Do not include the absolute uncertainty. So we don't need it. So just find out y is equal to mx plus c using your best fit coordinates. I opted to use these points. 0.91 equals to 0.88 times 10 to the power 4 times the gradient plus c. I get a value of 1.65 as my y-intercept. Next, I've been asked to find out the values of r and I naught using the initial formula. So we know that minus t by r is our gradient. So just input the value of time here and the gradient value, right? So you can get rid of the minus sign and we get a value of r is equal to 3.55 times 10 to the power 5. Your values will not completely match mine, but it will be along these lines, yeah. And the unit for r is ohms clearly, and ln I naught r is equal to the y-intercept. So check if the y-intercept has any powers. V has no powers, okay, so we don't need to bring back anything. So I naught r is equal to e to the power y-intercept, and I naught equals to e to the power y-intercept divided by the value of r that we just found. So I get a value of 1.46 times 10 to the power minus 5 amperes, the SI unit of current. Okay. Next, percentage uncertainty in R. What does R depend on? It actually depends on the y-intercept and I naught. Sorry, my bad, R. R depends on the gradient and T. So this is the uncertainty of gradient 0.39 by 8.44, and the uncertainty of T is 1 by 30. So just write those down times 100%. I get 7.95%. 1 by 30 plus your answers, your del gradient by gradient times 100%. And then the experiment is repeated with the same value of t 30 seconds. Determine the combined capacitance that gives a value of 1.20 volts. Okay, so you write this again. Ln 1.20 equals to the gradient. So just replace minus t by r by the gradient, which is minus 8.44 times 10 to the power minus 5 times 1 by c plus 1.65. So you bring 1.65 to the other side, you get a negative value. You can get rid of the minus signs, and C will actually be equal to gradient divided by this value on the left hand side. So it is gradient divided by ln V minus 1.65, your y-intercept. So I am getting a final value of 5.75 times 10 to the power minus 5 farads. Okay, so guys, that has been it for this paper. Hopefully it was helpful. If you do like the content, please do remember to subscribe to the channel, like the video, share with your friends. And quick shout out to my top tier patron for the month. We have Dewa still supporting me. He is from Indonesia, and he has his exams coming up just like you guys on the May-June 2024 session. So hopefully he does well, and so do you guys. He actually got country highest recently, the Cambridge Learner Awards. He's an amazing student. Anyway, if you want to be featured on the end page as well, you can support me on Patreon. It actually helps a lot. And you get access to one-on-one meetings with me via Google Meet every month, once or twice. So that has been it for this paper. Hopefully I helped you guys. I will link the paper for ON 23 9709 paper 51. Sorry, it is 9702 paper 51 or 9702 paper 53 up here, and the paper for May-June 2023 9702 paper 52 down here, and the playlist for physics paper 5 up here. And remember to hit the subscribe button. See you guys. Bye bye.